see the problem is what? The problem is following. The Bank of Bath issues coins with an H on one side and a T on the other. Harry has n of these coins arranged in a line from left to right. He repeatedly performs the following operation. If there are exactly k is greater than 0 coins showing H, then he turns over the kth coin from the left. Otherwise, all coins show T and he stops. For example, if n equals 3, the process starting with the configuration THT would be. Okay, so here let's see what we have. K here is 1 because we have one H. So we turn over the first coin. So it changed to HHT. Now, here we have two H's and we should change the second coin. We should turn over second coin. It changed to HTT. Now we have one H, so K is 1, and we turn over first coin and we reach TTT. Here all coins show T and we stop. And after 1, 2, 3, after 3 operations we stop. And part A, show that for each initial configuration Harry stops after finite number of operations. And part B says for each initial configuration C, let L of C be the number of operations before Harry stops. For example, L of THT, the number of operations to reach TTT is 3 and L of TTT is 0. Determine the average value of L of C over all 2n possible initial configurations. As we have 2n possible initial configurations, because each one it can be T or H, 2 times 2 times 2. Each one has two cases, T or H. So we have 2 to the n possible initial configuration. And now, at first, let's solve part A. In part A, we want to prove that for each initial configuration, Harry stops after a finite number of operations. So suppose that at first we have, for example, SHs, and we want to say after for example, some number of steps, we can reach S minus 1H, and then similarly we can reach S minus 2H, and so on. So we can reach 0H and the things that we want. So suppose that we have SH, the number of H equals S, and now we want to say that after one step, two step, or more finite step, we can reach this case, the number of H equals S minus 1. So if the S place is H, then we can say that, okay, so we change it to this, the S will change to T, and then here the number of H's is S minus 1. So in this case, the S place is H. But let's consider the other cases. So if we consider other cases, suppose that the S coin is T. So here we change it to H. Now the number of H is S plus 1. So we go through this. So if this is H, so we consider at first case 1. Case 1, we consider that the S is H. In case 2, we consider that the S place is T and the S plus 1 is H. So in this case, suppose that we have TH, HH, we change this place to T, and the number of H again is S, so we change it to TT. Now here the number of H is S minus 1. So we've reached what we wanted. So in general, let's consider the case that we have, for example, from ST, S plus 1T to S plus, for example, MT, and we can say that we have at least one edge. We reach at least one edge from S place, because we know that the number of edge here is S, and here the number of edge here is at most S minus 1. So we have at least one more edge. So we can say that we reach edge, for example, in S plus M plus 1. And now let's see what we have now. At first we have S edge, so we change it. Then we have S plus 1 edge, we change it. S plus M edge, we change it. And then we change this edge to T, because here we have this. So then when we change this edge to T, we have one less edge, so we change this edge to T, then we change this edge to T, this edge to T, and now in this case, after some number of steps, we reach this, and then in this case, the number of edge is S minus 1. So we proved that after some number of steps, we can reach from the case that the number of edge is S to the case that the number of edge is S minus 1. So similarly, we can reach the case that the number of edge is S minus 2, and so on until the number of edge equals 0. So after finite number of steps, Harry stops. Okay? This was part A, and now in part B. For solving part B, we solve it with recursive sequence and considering small examples. So here, and also we will consider the most important idea for solving recursive sequence. Also in IMO 2011, we have another problem that's related to recursive sequence. We use the same idea. So now for this problem, we want to learn two useful ideas. One idea is considering a small example. The second idea is how to solve recursive sequence problems. Most important idea in recursive sequence problems. So let's see. If n equals 1, so we have L of t and L of h. L of t is 0 and L of h is 1. So the answer is, suppose that we consider it an, the mean of all these L's. So A1 equals 0 plus 1 over 2. Mean of these two cases is 1/2. Now let's consider when n equals 2. So L of tt equals 0. So L of tt equals 0, L of th. So let's see, th change to HH, change to HT, change to TT. 1, 2, 3. 3. L of HT is 1 because we reached TT, and L of HH is, we change it to TT, it will be 2, and A2 equals 3 plus 1, 4 plus 2, 6, 6 over 4. And we've considered these small examples. Now we move to general n, and we want to consider how to solve a problem, recursive sequences problem. So let's see. For an, we consider that n refers to what? N represents what? N represents the number of elements. Okay, so here, and always always when you see that the n refers to what, n represents what, you consider the first element or second element. For example, if n in a problem represent the number of columns, consider first or last column. That's the most useful idea in recursive sequence problems. Here, n represents what? N represents the number of coins. So let's consider first or last coin. So if first coin is, let's consider these cases. If first coin is h, then we can say that, okay, if I consider this, then here we at the number of edges in all. If we want to, for example, look if the number of edges in all is f, is for example t, the tth coin here is t minus 1th coin here. So when we ignore this, if here we have t minus 1, for example, consider that in this rectangle the number of edge is t minus 1. Okay, so the number of edge in all is what is t. So if we want to change, if we want to select the tth place in rectangle, it will be t minus 1th place. Okay, because t minus 1th, if I consider this is 1, if I consider t minus 1th place, it will be t place. So here we can say by induction, also you can use induction, you can say, okay, I will reach t, or we can say part b. By this case, we can say we can reach t, and in one step we can reach t. Okay, so because the condition of the problem was satisfied in this case, because when we have t minus 1 edge here, we change t minus 1th place here, and now the number of ways we want to consider the number of steps that we've used here, we can say, okay, an minus 1, we have here, we want to count the number of ways, times 2 to the n minus 1, it will be the number of steps here, and for each of them we have one more because we changed this edge, so plus 2n minus 1, and we know for all of them the denominator is 2 to the n. So we've considered the effect of strings that the first element is h. Now we want to consider the cases that the last element is t. If we consider this, we can say again all the conditions are satisfied in this rectangle, because if the number of h is t, for example, this is, for example, let's consider this w, then you change the w because this is t. It has no effect on the rectangle, so you change it to, for part A, it changes to t. The last element is t, and we don't change the last element because if we want to change the last element, the number of h must be n, and we know that the number of h is at most n minus 1, so we don't change the last element. So in this case, it will be an minus 1 times 2 to the n minus 1, the number of steps, over 2 to the n. And now we've counted the ways, the number of strings that starts with h and also ends in t, but we need to find the number of elements that start with t. Okay, so let's consider the rest of them. We've counted the number of strings that start with h, and now we want to count these things, start with t and end in h. Okay, if we consider this, again we can say if the number of h's in all is, for example, the number of h in all is z, then we can say the number of h here is z minus 1, and we change the zth coin in rectangle is z minus 1th coin because it starts with t, so all the conditions are satisfied in this rectangle. In this rectangle, if we have, for example, z minus 1h, then we change the z minus 1 coin. So we reach t, and the last one is h. Then we change, because we have one h, we change this, to change all of them to h. And then we reach t. At first we change this one, and then this one, we reach this. So here, from reaching from this string to this string, n minus 1 step, and here n step. So it will change to a for this part an minus 2 times 2n minus 2. It will be the number of steps because this is mean of L of C. If we multiply by 2 to the n minus 2, it would be the number of steps plus n plus n minus 1 2n minus 1 times 2 to the n minus 2 over 2 to the n. And now we can say we found t to the h, and if we add up all these, so we need to subtract the strings that start from with h and end in t. And if we consider these cases, again we can say if the number of h's, for example, here is g, then we can say the number of here h here is g minus 1, and the g coin in all is g minus first coin here. And now we can say that we reach from this part to h, t, all of them t, and in one step we can change all of them to t. So it's one step, first one step, and now it will be a n minus 2 times 2 to the n minus 2 plus 1 for each of them, 2 to the n minus 2, all over 2. So let's see what we have. Starts with h and in t, so an is the number of string. Consider it start with h and in t, and start with h only, and then the number of strings, that last one is t. And if we subtract the common thing, and then if we add up t and consider start with t and end in h, so let's see, do we count all terms? If we start with h, we count it. If we start with t, we count it. If it ends in t, we counted that. So the strings that we didn't count is the string that start with h, with t, and ends in h. So we need to add up them, and also we need to subtract because we've counted these cases. But at first, it's an minus 1 times 2 to the n minus 1. It will be an minus 1 half plus 1 half. Okay, it will be an minus 1 plus 1 half. And the next one is an minus 1 half. An minus 1 half. And now let's consider subtract h and t. An minus 2 fourths plus 1 fourth. An minus 2 plus 1 fourth. And the next one is an minus 2 fourth plus 2n minus 1 fourth. An minus 2 plus 2n minus 1 fourth. We know that we can cancel these two things. And now what we have is an minus 1 plus 1 half minus 1 fourth, 2n minus 1 fourth plus 2n minus 2 fourth equals an minus 1 plus 2n fourth equals an minus 1 plus n half. So let's check. We said that a1 equals 1 half, and just for checking you need to write a1, and for checking let's check a2. We found that a2 is 6 over 4. So let's see, if we use this one, 1 half plus 1 is 3 over 2, it's 6 fourths. Now that's true, so let's find an by telescoping rule. An equals an minus 1 plus n half. So we can say an minus an minus 1 is n half, and until a2 minus a1 is 2 half, and if we add up all these, an minus a1 is 2 to n over 2, and a1 is 1 over 2, so an is 1 plus 2 plus 2n over 2, and it will be n times n plus 1 fourth. And if we check, we will see a1 is 1 times 2 over 4, 1 half. a2 is 2 times 3 over 4 is 6 over 4 as we found. So we found an in general. So if we review, we solve these problems with somehow invariant, defining function. Function was number of edges, and said that this function is decreasing, and we solved the first part with invariant. The second part, generally we use that with recursive sequence, and as I said, in all recursive sequence, most of them, around 90% of them, if you want to solve, see n represent what, and for example here, n represents the number of coins, consider first or last coin. Sometimes both of them are needed. Here we've considered both first and last coins, and we've reached the answer.